What does it take to protect satellites from laser interference in Earth's orbit? In this episode, we are joined by Tim Rebold, lead systems engineer at NASA Goddard Space Flight Center, who shares his journey into aerospace engineering and the groundbreaking work behind ICESat-2's laser safety system. From orbit modeling to mission planning, Tim helps keep space safe using the Constraint Analysis and Monitoring System, also known as CAMS, a tool designed to detect and prevent risky laser conjunctions with satellites like the International Space Station, also known as the ISS, Hubble, and beyond. Let's dive in. So the very first question I wanted to ask you was, can you please tell the audience about yourself and describe some of the projects you have worked on?
Sure. Hello all, I am Tim Rebold, born and raised in Cleveland, Ohio. I graduated with a master's in aeronautical and aerospace engineering from Purdue University in 2011. I relocated to Northern Virginia afterwards with my wife, another fellow Boilermaker and aerospace engineer, for her career to start and to raise our two children. Not long after that, I started my career with Emergent Space Technologies in support of NASA Goddard in Maryland. Fast forward 13 years, the company I work for was bought out by York Space Systems, and our family, now with 4 kids after adding twins, has relocated to Colorado Springs towards the end of the pandemic. This move across the country was for my wife to start her job and for our family to be closer to the outdoor activities we enjoy. Lucky for me, I became employed by SSAI during the Emergent acquisition, and I continue to support all the same Goddard tasks that I am passionate about. My work at Goddard involves supporting remote sensing missions with instruments aboard aircraft, spacecraft. My technical skills and expertise involve orbit and attitude determination, orbit design, modeling and simulation, mission and science planning, space situational awareness, as well as instrument calibration and proposal work. The majority of my operational wisdom and expertise has been gained from the 2 current NASA missions, ICESat-2 and GEDI. The Ice Cloud and Elevation Satellite 2, or ICESat-2, was launched in September of 2018, and it was designed to precisely measure the changing heights of Earth's ice sheets, glaciers, sea ice, and land surfaces. Using the Advanced Topographic Laser Altimeter System, or ATLAS, the satellite emits a strong laser pulse 10,000 times a second and measures the time it takes for the light to bounce back from Earth's surface. This allows us to calculate the elevation with remarkable accuracy. The data we collect will play a crucial role in understanding how ice loss from Greenland and Antarctica contribute to sea level rise and how seasonal snow and sea ice change over time. By providing high-resolution data, the mission supports research, improves ice sheet models, and contributes to the broader understanding of our Earth's cryosphere. The Global Ecosystem Dynamic Investigation Mission, or GEDI, is a NASA-led Earth science mission, and it was deployed on the ISS in December of 2018, shortly after ICESat went fully operational. The GEDI mission is designed to map forests and landscapes in 3 dimensions using a full waveform LiDAR technology. As the instrument measures the time and intensity of returning photons reflected from the canopy and the ground, it builds detailed vertical profiles of forest structure with unprecedented resolution. GEDI was initially designed for a 2-year nominal window, but it has since been extended all the way up until now with a brief 1-year shutdown in between, so we can continue to leverage the valuable data products. The mission supports critical research into global carbon balance, habitat and biodiversity assessments, and improvements to digital elevation models. Researchers and scientists integrate GEDI's 3D forest structure maps with complementary data sets from other missions such as Landsat to advance our understanding of ecosystems via forest management and environmental conservation.
Wow, that is absolutely fantastic, Tim. That's all very interesting in terms of the work that you do and your contributions to various projects and initiatives. So I greatly appreciate you highlighting that. Tim, my next question I wanted to ask you was, you work at the intersection of advanced mathematics, simulation, and aeronautics, fields that are rapidly being transformed by AI, as I'm sure you have probably seen. In regards to that, based on your experiences, how is artificial intelligence enhancing the way SSAI approaches modeling and optimization in aerospace engineering? And what possibilities does it open for the future of flight and national safety?
For SSAI, artificial intelligence is going to open up possibilities across all stages of a mission's life cycle. From the early development phases of a mission, AI could be used to accelerate the pace of trade studies to optimize the design of a spacecraft, as well as the other many key processes involved. The iterative nature of design across all subsystems and within all disciplines could be improved with the introduction of AI. Operations is another critical aspect of the mission that can benefit with the use of AI. Advanced machine learning algorithms can analyze telemetry and onboard sensor data to predict component failures before they happen. This will increase the reliability and reduce the downtime for spacecraft. Anomaly detection or prevention, coupled with the ability to respond quickly, if not prevented, are other important features that can be enhanced with the introduction of AI. Both of our major missions have suffered from anomalies, and some have resulted in significant downtime, with the spacecraft being in safe mode, unable to collect science data. Folding AI into the missions can help us become more robust and efficient when presented with these challenging circumstances. I myself have firsthand experience with daily operations supporting the ICESat-2 mission, and I can say that being a satellite operator engineer can be a lonely spot when problems occur. In these moments, it can seem that there's an overwhelming amount of information to process, or quite the opposite at times, that there isn't anything remotely valuable to aid in making quick and quality decisions. Instead of replacing engineers or operators, AI could function as a co-pilot, potentially offering risk assessments, course corrections, or valuable system diagnostics during missions. Other potential benefits of incorporating AI into our engineering culture include support of autonomous systems, optimism, and enhanced national security. Think of adaptive mission planning, obstacle avoidance, or formation flying with minimal human input, or the onboard identification of more fuel-efficient paths based on solar storm conditions, or the dynamic scheduling and management of satellites in a mega constellation. AI could also help process, interpret surveillance, recon, and environmental monitoring data more efficiently. For national defense, this means faster threat detection, improved decision-making under uncertainty, and support for resilient aerospace systems in contested environments. Finally, the biggest potential benefit using AI so far in my field of work comes in the processing of analyzing the vast volumes of data obtained from the instruments and sensors deployed by these remote sensing missions. Machine learning, neural networks, and similar algorithms are being used to develop models to approximate complex physical systems, which greatly reduces computational burden and enhances scientists' predictive tools. One can imagine how the immense amounts of data that are collected from ICESat will allow for better models to be developed. What could this lead to in the future? The ability to process environmental data in real time and reliably predict or forecast severe weather conditions would give longer lead times to plan and act accordingly, improving the outcomes of many lives on this changing planet. In summary, AI is enabling SSAI to move toward a future of smarter, faster, and safer aerospace engineering.
Yeah, I was going to say, Tim, you brought up a lot of excellent points in regards to artificial intelligence and, also machine learning as well. That definitely has grown over these last several years, and it will continue to be something that will continue to advance. It's just amazing, as I think you can agree, all the technological advancements we've had over the last, 50, 60 years or so. So I definitely appreciate you highlighting some of the benefits with AI currently. And Tim, my next question I wanted to ask you was, at SSAI, We're known for turning advanced modeling and simulation into real-world solutions that improve lives and support public health. Given your expertise in numerical simulation and applied mathematics, how have these tools been, or how could they be, used to support environmental monitoring and resource management, such as forest health, air quality, or land use protection?
The majority of the projects and missions I've worked on involve firing a laser at Earth's surface with enough power to reflect back and return to the instrument with enough energy to be discernible from background radiation. One of the most interesting and challenging projects I have worked on concerns national, if not world security, and it involves operating ICESat-2's powerful lasers responsibly and ensuring the safety of everything in the space environment. The Constraint Analysis and Monitoring System, or CAMS, was implemented as an ICESat-2 ground system element to perform mission planning and spacecraft safety monitoring. Spacecraft safety monitoring includes both monitoring instrument health as well as space asset laser conjunction screening. Related to NASA's CARA, the well-known and critical service that screens for potentially catastrophic collision events in low Earth orbit, CAMS operates in a similar manner, screening thousands of space objects, including maneuverable and non-maneuverable payload, as well as debris for potential laser conjunctions. ICESat-2's predecessor, ICESat-1, did not perform laser conjunction screening, and given the sparse history in this field, many of the CAMS capabilities that were developed by our group are pioneering, if I am allowed to brag. Because CAMS also performs mission planning, it has the exact science timeline on board. With this timeline, CAMS can accurately model and predict both the position of the spacecraft as well as the pointing of the laser altimeter using sophisticated algorithms that were developed and validated pre-mission. With these predictions, CAMS provides precise monitoring of instrument health and performs space asset laser conjunction monitoring. Furthermore, CAMS determines and implements alternative plans to prevent instrument health violations and mitigate those potential laser conjunctions. A very early study conducted well before CAMS was even considered attempted to estimate the frequency of laser conjunction events. The study determined that these events would be rare over the course of an entire mission, but the study had a critical flaw. It assumed perfect knowledge of orbits under consideration, along with the instrument's pointing. Uncertainty or error was never considered in the study at all. For the design and implementation of CAMS, rigorous and faithful error modeling is perhaps the most critical aspect of the system. Many of the objects in space that are screened use two-line elements for generating orbit predictions. Few assets or missions provide us with their own accurate predicts. The ISS falls on this short list, and these predicts are much better than TLEs. These TLE predicts tend to accumulate kilometers of uncertainty or error after a day and become unreliable after more time. You can imagine the orbit as an elongated ellipse or even a balloon or blimp of certain size that is attached onto an orbiting spacecraft. As this spacecraft passes under ICESat, if any of the 6 individual beams hits this balloon, at any point, a laser conjunction has been detected. Pre-mission simulations using realistic orbit error soon produced detected conjunctions by the dozens. We thought we were in big trouble leading up to the mission start. It would not be feasible to react to all these potential conjunctions. At this point, a risk assessment could be used to make an informed decision. Given the input error models used to screen and detect a conjunction, these same errors could be used to determine the probability of such an event happening. Again, similar to the process CARA uses for collision assessment, CAMS computes a probability of the conjunction occurring to determine if the risk warrants action. Adopting the same probability threshold that CARA uses for collision avoidance planning, we found that only a few events per week would require action. In these cases, we could simply just turn off the laser as our go-to action. Over the course of ICESat-2's mission, space assets who have required lasers to be either pointed away or turned off most frequently include both the ISS and Chinese space stations. Given these objects are not shaped aerodynamically, meaning they experience more complicated and time-varying drag patterns, Their orbit predicts tend to have much larger errors than most space objects. This means, visually speaking, that they're flying around under us as big, swollen, ready to burst balloons. Other notable objects requiring mitigation include the Hubble Space Telescope, NASA's WISE mission, and countless transitioning Starlink satellites. So finally, speaking of national security, one of our very first conjunctions came in, and the object's identity was not immediately recognizable to anyone on our operations team. A quick web search using the object's catalog ID informed us that it was a Korean satellite that was going to pass under our laser the next day. So we turned the laser off, and ICESat-2 has been safely and responsibly operating for almost a decade now.
Wow, I was going to say, Tim, that's very fascinating to hear. I've been learning some cool, interesting facts in regards to ICESat-1 and then also ICESat-2 as well. So I really appreciate you breaking this down for our audience and viewers. Lasers are very cool. I think we can definitely all agree with that. So Tim, like I said, I really appreciate you highlighting a lot of that. And Tim, my final question I wanted to ask you was, and this is a fun question that just as a side note, but the question is, if you could simulate anything in the world, just for fun, no budget or boundaries, what would you model and why? Would it be something in aeronautics, nature, sci-fi, or, maybe predicting the perfect coffee to productivity ratio?
Fortunately for me, most of my engineering passion and curiosity is already satisfied with my current job. From implementing new and unique filters for attitude or orbit determination to simulating the most interesting aspects of missions and estimating performance, I've had the opportunity to please my inner engineering nerd. In addition, there's no short supply of challenges, problems to keep me engaged. But I wouldn't be able to call myself a true Coloradoan if I wasn't obsessed with at least some of the state's most celebrated hobbies: hiking, biking, fishing, Subaru ownership. I find myself enjoying all of these to different degrees, but my move introduced me to perhaps my new favorite hobby, skiing. After
Man.
4 seasons, I grow in love with the slopes more and more every year and start dreaming of powder around late August when the kids get back to school. Working on the challenges and logistics of traffic, lodging, and work, I do find myself skiing more often than not in just plain average conditions. I know this must sound petty, and I am actually really grateful, but I did find myself skiing on ice and concrete crust more than ever last season. This must frustrate anyone who lives and skis on the East Coast, where skiing is more akin to ice skating. But powder does truly elude me for most of my trips into the mountains. I can count on a single hand the number of times I was grinning ear to ear as I floated and slashed through some majestic pow. So, with unlimited computing power, resources, and budget, perfect weather predictions extending not just hours, but days and maybe, we dare say, weeks into the future would allow me to travel and plan more confidently, which would unlock more powder days and create endless grins on the faces of the Rebolds. Thank you all.
That was excellent, Tim. I really appreciate you highlighting, as a side note, some of your passions and hobbies, especially since you and your family moved out to the Colorado area. It's definitely beautiful out there, and that's great that your current role, really benefits you and it benefits your engineering passion as well. I really appreciate you highlighting a little bit about that. And Tim, with that, again, I just wanted to thank you so much for taking time out of your very busy schedule to talk with me today. You are truly a rock star who is really making an impact and a difference globally, and everybody around the world is going to continue to be fascinated by the great work that you and your team do. Please definitely keep us posted in terms of some continued insights that come, especially with ICESat-2 and some additional innovations that come, especially with your role in artificial intelligence. And we cannot wait to highlight that.
Thank you.